Speaker should try. ಹೇಳ್ಬೇಕಾಯ್ತಾ ಹಾಗೆ 2016 ಇದು ಮಾಡಿದ್ದೀರಾ ಆನ್ಸರ್ ಇದು ಮಾಡಿದ್ದೀವಲ್ಲ 2016 ಇಂದ 2 ಮಾರ್ಕಿದ ಕ್ವಶನ್ ಮಾಡಿದ್ದೀವಿ ಈಗ ನೆಕ್ಸ್ಟ್ 2016 ಇಂದ ಇನ್ನೊಂದು 2 ಮಾರ್ಕಿದ ಕ್ವಶನ್ ಉಂಟು ಅದನ್ನು ಮಾಡಿ ಸಿಮಿಲರ್ ಟೈಪ್ ಓಕೆ 2016 2 marks set 3 let us see a cylindrical steel rod rod 0.01 meters in diameter and 0.2 meter in length is first heated to 750 degrees centigrade and then immersed in a water bath at 100 degrees centigrade. The heat transfer coefficient is 250 watt per meter square Kelvin. The density, specific heat, the specific heat, and thermal conductivity of steel are rho is equal to 7801 kg per meter cube, C is equal to 473 joules per kg Kelvin, and K is equal to 43 watt per meter Kelvin respectively. The time required for the rod to reach 300 degrees centigrade is dash seconds. Do not refer to the formulas which is at the back and do it. It's practice. And if you want, put a timer. See that how much minutes you'll be able to solve that question. And use gate calculator, not other calculators. Yeah, got the answer? Super. Who got the answer here? Got the answer? Super. So you see, it is less than 2 or 3 minutes. You can solve it. 1 minute. You can solve it. Is it not? Huh? Correct? Everybody got it? So that's it. So initially it seems difficult. When you do similar question again and again, you get the confidence. And once you keep on doing it, okay, and you don't forget now. Now you should not forget. That's the end. And in the exam, you have to remember. Okay. So inhaling 43 point is equal to 43.49, 43.5. That's the right answer. Right? Everybody got it? Got it, Mr. Money. Ready, bidding. Sujitik Banta? So I want everyone to get the answer. Yeah. Super. ಭರತಿಗೆ ಬರಲಿಲ್ವಾ ಆನ್ಸರ್? ಭರತ್ ನಿಶ್ಚಲ್ ಬರಲಿಲ್ವಾ ಆನ್ಸರ್?
Sir, 43.5.
40?
43.5, sir.
ಕರೆಕ್ಟ್. ಸೊ ಸೊ ಹೀಗೆ ಈ ಥರ ಕಾನ್ಫಿಡೆನ್ಸ್ ಬರುವಂಥದ್ದು ನಿಮಗೆ ಬರಲಿಲ್ವೇನ್ರಿ? ಟ್ರೈ ಮಾಡಿ. ನಾನು ಹೇಳಲ್ಲ ಆಯ್ತು. ಯಾಕೆ ಹೇಳೋದಿಲ್ಲ ಅಂತ ಹೇಳಿದ್ರೆ ಏನೋ ಚಿಕ್ಕ ಮಿಸ್ಟೇಕ್ ಮಾಡಿದ್ದೀರಾ. ನಿಮಗೆ ಕಾನ್ಸೆಪ್ಟ್ ಅರ್ಥ ಆಗಿಲ್ಲ ಅನ್ನೋ ನನ್ನ ಭಾವನೆ ಇಲ್ಲ ಅಲ್ವಾ? ನಿಮಗೆ ಕಾನ್ಸೆಪ್ಟ್ ಅರ್ಥ ಆಗಿದೆ. ಏನೋ ಒಂದು ಕ್ಯಾಲ್ಕುಲೇಷನ್ ಮಿಸ್ಟೇಕ್ ಮಾಡಿದ್ದೀರಾ. ನನಗೆ ಹಾಗೆ ಅನಿಸುತ್ತೆ. ಕರೆಕ್ಟಾ? ಇಲ್ಲಿ ಒಂದೇ ಒಂದು ಮಿಸ್ಟೇಕ್ ಮಾಡಿರೋ ಚಾನ್ಸಸ್ ಏನಿರುತ್ತೆ ಅಂತ ಹೇಳಿದ್ರೆ, you would have taken V by A as not R. You would have taken R by 3. It's a cylinder. What you should take? You got it. Is it not? You get volume by area. You did, and then you did it. Volume by area is equal to length. What is the length? Okay, you did the volume by area, and then you calculated that L. Fine. Then you should get the right answer. No, you will not get 0.2 meter. You get 0.25 meter. You've done a mistake there. When you say, yeah, it is a 0.2 meter length, is it not? Okay. Can you take that length? No, you cannot. You took that length. That is not the case. When you consider t minus t infinity divided by ti minus t infinity is equal to e power, if you consider here, minus ha by rho vc into t. Now you have to take a by v. What is a by v you took? You took it like that. So what did you take a by v as? You took it as 0.2 meter. L 1 by L is equal to a by v, or L is equal to v by a. What did you take v by a as? What is the volume? Pi r square L divided by area pi r square. Is it not? Correct. So length is 0.2 meter only. So no problem. No. Wait a minute. No. Volume by area. Volume is what? Pi r square L. And area. Here, this is a mistake. 2 pi RL. There is a mistake. You have to take 2 pi RL. That is a mistake. You understand? If you take pi r square, it is not the area, it is the surface area. Mistakes. So we can learn from others' mistakes also. We can learn from our mistakes also. Correct? So this can happen to anyone. Okay. Next question. So speed is the key now. I know you know the concept. Now speed is the key. Okay. Now next. This has come in 2017 for 2 marks. Let us see what is that. A metal ball. A metal ball of diameter. Metal ball of diameter 60 millimeters is initially at 220 degrees centigrade. Okay. The ball the ball is suddenly cooled by cooled by an air jet of 20 degrees centigrade. The heat transfer the heat transfer the heat transfer coefficient the heat transfer coefficient is 200 watt per meter square Kelvin. The specific heat the specific heat the specific heat thermal thermal conductivity and and density of the of the metal ball are 400 joules per kg Kelvin, 400 watt per meter Kelvin, and 9,000 kg per meter cube. What could be the thing respectively? It may be a copper based alloy, is it not? Seeing the densities and all those things. The ball temperature, the ball temperature, the ball temperature in degree centigrade after 90 seconds will be approximately a 141 b b 163 c 189 and d 210. Let's get last. बनता बनता नहीं है मान 210. Okay. For you 140. This answer is 141 only. So you did some calculation mistake. You have to be careful. When it is easy, you have to be doubly careful. Don't think that you have completed the syllabus and you know the concept doesn't mean that you are right always. There is human errors which shall happen. And if possible, write down the mistakes what you do when you solve problems. You see what is the mistakes you have done. Like last time when our David did a problem, he used area that you write somewhere. This was the mistake which was done. What was the mistake?
Get it to about 20 somewhere. So calculation e to the power.
Okay.
Added a extra 10 somewhere. So calculation. Other option.
So especially when you do a calculation mistake, if that is in the option, you will not review it. So even if it comes later on, you have to review your answers. Okay. In case you say all the questions you know is over by 2.5 hours, say, then half an hour you have to see the calculation again, do the calculations again. That is one of the ways you can reduce the mistakes. Because once you go the mistakes, you are in that mood that it is right. Look at it again, whether it's right or wrong. Second view in the last half an hour. So that whatever you know, you have not done it wrong. Okay. So last question, I will do unsteady heat conduction a bit later. Okay. I will skip that now because I want to do it because only one question has come on that. Okay, till now in 2016. Afterwards, it has not come. Okay. So what I will do is I will do it as a miscellaneous. Keep in mind. So write that there are some topics which are there, octane, cetane numbers, which has not come, but let us do it at the end. Unsteady heat conduction, okay, with high Biot number, you say. Whatever is major one, we will complete, which comes a lot of times. Okay, last question. Then we will go with convection. This has come in 2020 gate, okay? 2020, okay? 2 marks, set 1. A small metal bead, a small metal bead, radius zero point 0.5 millimeters, initially at 100 degrees centigrade when placed in a stream of fluid, in a stream of fluid at 20 degrees centigrade, attains a temperature attains a temperature of 28 degrees centigrade in 4.35 seconds. 4.35 seconds. The density, the density and specific heat, the density and specific heat of the metal are 8,500 kg per meter cube, and which is the material, can you tell me? 400 joules per kg Kelvin. Which is the material? Which material can be? Huh? Steel? Uh, no, small metal bead. It is not said steel. Huh? Steel, what is the density? It comes between 7,200 to 7,800. It cannot be above 8,000. When it is above 8,000, it is copper. Okay. Silver is much higher, is it not? Silver is 11,000 or something like that. Silver density, you see, one second, somebody do a Google search of silver density. If the bead is
30, 10,500.
10,500, nearly 11,000. Okay. Considered as lumped system, the convective heat transfer coefficient in watt per meter square Kelvin between the metal bead between the metal bead and the fluid stream and the fluid stream is A 149.9, B 449.7, C 283.3, D 299.8. Tell me what's the answer. Don't see back. Hmm? D. Yes. Correct answer. You see how fast you're doing it? Not even a minute. Not even a minute. That's how practice is. We'll stop here. We will go to convection. Okay. So unsteady heat conduction, there is no questions. Only one which has come, which can be done in general. Okay. But later on we will see. One question in 2016. Okay. 2022 we will see whether the question has come. Okay. Banta, confidence banta. Answer one ಕೊಡಿ. ಆಯ್ತಾ heat transfer ಅದೇ ಆಗುತ್ತೆ. In heat transfer, you think you don't understand, but once you start solving problems, it becomes so easy that you will never leave heat transfer. Heat transfer is very important. It's easy mark scoring, but difficult to understand first. You put that initial efforts in understanding, then heat transfer is easy. And that I'll have. Entropy, we have done this. This is all three combined together. Heat exchanger is fantastic question. This is. They are asking heat exchanger in the open heart surgery. Okay, so we are worried about heat exchangers here. We are going to do this problem. Fantastic one being asked. Saying that heat exchanger is not just in your heart, it is in your heart and lungs. It's a heat exchanger. Lung is a good heat exchanger. Yes. This we have done last time, is it not? Yeah. So no more questions on this being done. So this time you may expect a question on this topic, because last time this topic there was no question. Okay, so just expect. Okay, so done. Shall we go for it? Now we'll go with convection. So new, I will change this to conduction. Okay, say I will change to conduction complete. Okay, then I will do convection in a separate PPT. This is convection, sorry, conduction. Conduction. A basic concept plus conduction. Basic concepts and conduction. We will have the second one. We will go convection, heat transfer, convection. After convection is over, then we will go with radiation. Convection maybe I will take around 10 classes, 10 hours of classes is required for convection. Okay, after 10 hours of class, convection is completed. Another 12 hours for 10 to 12 hours for radiation, and around 4 to 5 hours for heat exchanger design. Okay, then the whole thing is completed. Okay. Generally, I can complete, if I go fast, I can complete the whole heat transfer within 40 to 45 hours. But this time I have done a lot of, I do a lot of problems, as well as I will go slow. The reason is because you know the reason, is it not? The reason is because you will have the you will have both practice as well as understanding here itself. It's not just lectures. It's practice. You see, this if you are done by yourself, you would have taken more time. The confidence what you get now is because of the type of classes we are doing, and the breaks, the pauses that I give, which allows you to think and ask questions. Had I not given you the pause and scope to think, then what will happen? You will say understood, sir, understood everything, and we'll complete fast. But then you will not get anything. Give me 2 minutes, students. So we are starting with convection, heat convection. Full topic, no? So I'll write it in heat convection. Today, what is the date? 21st November 2022, 12:11 p.m. Okay, we have started convection now. So let us change the color to black. Okay, so let us see what is convection heat transfer. We know there are the basics. I have told you what is convection heat transfer, is it not? And it generally comes with boundary layer theory. So from there only everything comes. Okay. So now here in convection, see, I will not go to the very deep as I have gone last time because I feel it's unnecessary. Later on, you will find it why. Okay. So only thing is that you will have the thermal boundary layer in addition to our in addition to thermal boundary layer we have hydrodynamic boundary layer. In addition to hydrodynamic boundary layer, you have thermal boundary layer here. That is the main thing. So two types of convection which we have told. First one is a forced convection, which we are going to do now. We are going to do forced convection first, and then we are going to see about pre-convection. Let us first do the forced convection. Okay. Now, in forced convection, if you see, there are two things. Let us take a flat plate. Okay. Over this flat plate, I am going slow purposefully now for you to understand the concept. Okay. Over the flat plate, you may have a velocity boundary layer. I will call this HBL. Stands for hydrodynamic boundary layer. Right, you know that, is it not? HBL, I will not say. It's hydrodynamic boundary layer. Means velocity boundary layer. Okay. You may have a thermal boundary layer. So thermal boundary layer, I will put it a bit higher. You will see this is thermal boundary and this is delta T. And this hydrodynamic boundary layer, I will write it as delta. Fine. Now on the let us define a dimensionless temperature, dimensionless temperature, which is defined in terms of this is x, this is y, a temperature theta, which is a function of x comma y, as so we are considering steady state only, no unsteady state here, it's steady state. Okay, as theta of x comma y is equal to t wall, this is the t wall minus t at any point divided by t wall minus t infinity. T infinity is the free, what to say, the flow which is coming here and hitting it. This is having a u infinity and t infinity as its properties. Understand? So now the boundary layer, okay, the boundary layer at the thermal boundary layer, at the thermal boundary layer, okay, theta equals 0.99. See, theta equals 0.99. So what happens? Tw minus T infinity, it implies Tw minus T is equal to 0.99 times Tw minus T. Make sense? That is thermal boundary layer. Very important, right? We have done non-dimensionalization in our in fluid mechanics. Similar non-dimensionalization will be done here. I will tell you how. Is this clear? Write it down neatly, students. Theta is equal to 0.99. It's a non-dimensional quantity. It does not have any units. It's a non-dimensional quantity. So it means the temperature difference between the wall and the incoming fluid, or the temperature between a point and an incoming fluid, if it is equal to 0.99 times the difference between the wall and the incoming fluid, then it is the boundary layer. We are on the boundary layer. That's what it means. I hope everyone understood this. Very important. Yeah, I cannot see this. See, because no, it's up. Students keep asking doubts. Or at least say yes. Online students. Are you clear? Is it clear, students? Have you written down?
Yes, sir.
Yes.
Ah,
Yes, sir.
very good. Because sometimes what happens is there is a there sometimes connection goes off due to some reasons. So I'll be continuing with my lesson. If you say yes, I'll be okay with that. Done. Ciao. Next. Now, see, till now we had gone with uh, heat. We have gone with conservation equation in terms of three equations are there. Okay, so we'll see governing equations. Governing equations for forced heat convection. What are the governing equations? First governing equation is mass conservation, which is that in two dimension I'm going to write, or three dimension should I write? Let us write in two dimension. What is that? Dou rho by dou t plus dou u by dou x plus dou v by dou rho u by dou x, right? Write it neatly. Dou rho u by dou x plus dou rho v by dou y plus dou rho w by dou z is equal to 0. What is this? This is continuity. Fine. Next, momentum conservation. If you see momentum conservation, we can write this as rho into du by dt. Correct? Density into du by dt is equal to, this is Navier-Stokes. When I say d, it means total derivative. How do we do acceleration? Okay, this is equal to, okay, so if you consider only x component, if you consider this is like this, or let me, okay, or, and then you have minus dou p by dou x plus mu into del square u, correct, del square u, correct, del square u plus rho g, correct. This is momentum equation, right, in the x component. So we will consider x component only. They can be y component, z component also. Similarly, we have x, or we will write this down. Okay. So dou dv by dt is equal to minus dou p by dou 1 plus mu del square v plus rho g. This is x, this is y. Similarly, dw by dt is equal to minus dou p by dou z. Write this down fast, students. Del square w plus rho g x, rho gz. This is y component and this is the z component. Easy. This is important here also. This is simple. This has to be there. In addition to this, there is energy equation, which is the continuation of heat conduction equation. In heat conduction issue, there is only conduction. Now that conduction is carried away, advected. So that advection has to be there in energy equation. That's what we will see now. I will do convection fast, students. Okay, I will not spend much time because that much is enough. Why to go with the MTech level? Not required. So sometimes we have to ensure that we do well in the gate. And whatever the base has to be built has been built in fluid mechanics only, so you don't have to worry. Okay. Done. Next. Next is, see, in case you have energy equation, let us see what is energy. See, in heat conduction equation, what was heat conduction equation? You had dou square T by dou x square plus dou square T by dou y square plus dou square T. Don't write. Let me finish this out, then write. Okay. Don't write. I told you not to write. Okay. Then what you had plus qg by k is equal to minus dou t 1 by alpha, right? Dou t by dou t, right? This was conduction equation. Agreed. Now, in this conduction equation, if there is no heat generation, in the absence, in the absence of heat generation, you can write it now, students. Heat generation. We may have, we can write, we can write in the absence of, is this minus here? No, right? I'm sorry, I made a mistake here, I suppose. Is it not? Minus is over here, is it not? Where is the minus there? Is there a minus there or not? Look at the heat conduction. No minus at all, is it not? It's all pluses, correct? Yes, it's all plus, no minus. Very sorry, right? So here, now you can write, we can write dou t by dou t is equal to dou square t by dou x square plus dou square t, oh, I'm sorry, here, alpha into dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square, which is equal to alpha into del square t. Correct? Now compare this with Navier-Stokes equation. Okay, compare this with Navier-Stokes equation. Comparing with x momentum. Let us write dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z is equal to minus 1 by rho dou p by dou x plus nu into dou square u by dou x square plus dou square u by dou z square plus dou square u by dou y square. I'm sorry. Plus dou square u plus dou z square. If we are neglecting gravity. Okay. If you compare this, you will see what are missing in this. Understand first. First understand. You can write it. Okay. What do you miss? In this, see, this is similar to this. Similar, analogous. This is similar to this. What is missing is this part and this part. Now, if you consider this part, what is happening? U is carrying U gradient. U is taking away the U gradient. Similar way here, V is carrying dou U by dou Y, or dou U by dou Y. Yes, gradient. V is carrying dou U by dou Y. There, W is carrying dou U by dou Z. Makes sense? So here, instead of U, if you put a T and don't consider pressure gradient, you get the energy equation. So the energy equation would be is carrying, I'll write dou U by dou X in small. So I'll take. Okay. Now, energy equation is given as dou T by dou T plus U dou U, sorry, dou T by dou X plus V dou T by dou Y plus W dou T by dou Z is equal to alpha into dou square T by dou X square plus dou square T by dou Y square plus dou square T by dou Z square. That's it. Very, 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 very important. That's it. Right. This would be our energy equation without heat generation, of course. This I will call it as, what is the number we have called till now? No numbers. So let us call this as 1. Okay. Let us call this as 2. We call this as 1 and this as 2 because that is important. Okay. Next, call this as 3. Call this as 4A, 4B, 4C, 4ABC. Fine. 2 was the small one at the thermal boundary layer because that's very important. You are defining thermal boundary layer. Okay. Next. Now this would be 5. Nothing else. This would be equation. So
So what about the pressure gradient here?
no pressure gradient. There's nothing. The pressure gradient is not causing the temperature. What is causing the transportation? The pressure gradient is causing the velocity. Okay, the pressure gradient causes velocity, and velocity causes transport. The same thing happens even in mass flow, what is a mass diffusion or transportation of mass.
Sir, here velocity causes temperature, sir, in convection.
No, 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 no.
So the boundary
Pressure
layer.
causes velocity. I'll repeat again. This is forced convection. This is not free convection. I'll repeat
Goes
again.
down, sir. When the velocity of the fluid is more, it affects the thickness of the boundary layer.
Yes, it does. Agree. No
Yeah.
backtracking on that.
Then there is no effect on temperature there.
When there is effect on velocity, there should be effect on temperature.
You said there is no.
I said what?
There is no pressure depends on velocity. Pressure gradient.
Pressure gradient depends on
Velocity.
no velocity depends on pressure gradient. And now here one thing I'll clarify. Have you written this down? Very good question he has asked. Now that's where engineering comes into picture. Okay. Online students finished writing? No. Let him finish.
But flow exists only when pressure gradient exists. Flow exists only when pressure gradient.
No, no, no. Flow can exist without pressure gradient also, provided it is pushed by some other things.
Okay?
Yeah,
Must be there to push.
exactly. Don't worry, write it neatly, write it neatly. No urgency here. This is the heart. So when you're making a baby, now you're making the baby's heart. Very important. So take as much time as you can. ಆಗೋಯ್ತಾ? ಸರಿ. ಈಗ now what is happening here is this. See, I guess yeah, I want you to respond. Okay. See,
Yes, sir.
if there is a flow which is stagnant, okay, there is a stagnant flow. The water is stagnant. Now, if you want this water to move, what you have to create? You have to create pressure difference. So without pressure difference, I don't have flow. Agreed?
Yes, sir.
So without pressure gradient, we don't have flow. First thing. Okay. But once there is flow, there is no requirement of pressure gradient. Once there is velocity, there is no requirement of pressure gradient. It will flow in the absence of friction, in the absence of viscous effects. Now, where does viscous effect comes? Viscous effect comes in pipes. Viscous effects comes in pipes. So if you have a flow which is happening, as it comes here, it decelerates because of viscous action. Got the point? So what is happening? The energy is reducing because of viscous action. Make sense? Now, To supply the same amount, everything has to go here, then the pressure has to be more. Otherwise, pressure, it loses energy. There is heating. So here pressure P1 and here pressure P2. There should be a difference. If there is no difference, it cannot go. It will go up till a level, lose its energy, and it cannot go further. Make sense? So when it cannot go further, there is a back pressure. It cannot do anything. It will stay there. So you need a pressure gradient. So in terms of when I said because of velocity there is pressure gradient, it means it does not mean that velocity causes pressure. Velocity can cause pressure gradient. When it's very difficult here. Okay. When can velocity cause the pressure gradient? Because it may suck something in. When you blow, then the pressure can come lesser. It is all dynamic actions. It can happen. It vortex. It can happen. It can happen even in a pipe flow or a channel flow. The velocity is coming here. It is creating a pressure. So velocity can create pressure. Pressure can create velocity. Pressure energy can be converted to kinetic energy. Kinetic energy can be converted to pressure energy. Of course, with losses. Of course, with losses. Because when velocity is there, there is losses. Because there is heat generation, there is viscosity. Clear? Now, in case of heat transfer, velocity, this velocity flow which is going, it can carry along with it something, is it not? It can carry a twig you put on the water stream, you put a twig, you put a leaf, it will carry the leaf, is it not? Similarly, it carries heat. The concept of convection is that this is heated and water is flowing here. What does it do? It carries this to a bigger position, other position. That is what is forced convection is all about. Agastya, is it clear now?
Yes, sir.
Very good. Okay. So that's how all the things are. This is about convection. Now in convection, we are going with something called non-dimensionalization. What do we go? We go non-dimensionalization of the whole Navier-Stokes equation as we go. When you say, so non-dimensionalized, non-dimensionalized governing equation we will see. We will see non-dimensionalized governing equations. So all are non-dimensionalized. I am going to give the last one. So everything is non-dimensional. Okay. So first one is continuity in two dimensions. I will say in 2D. Okay. Continuity is dou u by dou x plus dou v
So,
by
so,
yes, please.
so one thing here you compare with the x momentum, so energy.
Yes.
The same way you can compare with the y and z here.
Yes. Yes. Of course. Of course. Yes. So this is you can compare with that, yes, but energy is does not depend on this temperature, does not depend on the direction. It is a scalar equation.
Okay, sir.
Observe this here. This is a scalar equation, whereas this is a I component. This is the x component of the vector equation. The total equation is these three together. With this, we have to say I. This we have to say J. This we have to say K. If you write it properly, I have to write a rho into du by dt I plus dv by dt J plus dw by dt K is equal to minus of dou p by dou x I, dou p by dou y J plus dou p by dou z K plus nu into dou square u I, dou square v j, dou square w k plus rho into gxi, gyj, gzk. This is the total vector equation. Whereas if you consider this is a scalar equation because all these are scalars. All these are scalars. Make sense? Dou t by dou t. How it can be vector? Now what is this u? What is this? This is v dotted with del t. If you want to write it in a vector equation, you can write this. Okay, I'll write it here. Okay, so in vector notation, energy equation can be written as dou t by dou t plus uv dotted with del t plus is equal to alpha square del square t. Let this be 6. So you have to understand in terms of vector. Okay. So when you dot, you get a scalar. Hmm. I'm sorry, alpha square is not there. I'm very sorry. Alpha only. There's a derivation of this, students. You can see it later on in our and non-dimensionalization we have seen. Okay, so let us see non-dimensional equation. Done. Now non-dimensional equations. Okay, now non-dimensional equations. Now what we have to do is let us see non-dimensional equation in 2D, and we are going inside the, just a second, don't write. We are going with inside the boundary layer. Okay, so equations inside the boundary layer. We are going inside the boundary layer. So what are the equations we are going to have? We are going to have Prandtl's boundary layer equation. What we have done in Prandtl's boundary layer equation, same equation being non-dimensionalized. Make sense? So when you non-dimensionalize that, here one more thing. Wait a minute. Should I do this? 1 second, students. 1 second. Let me do the energy equation inside the boundary layer. It comes as, okay. Okay, let us not have non-dimensionalized equation. 1 second. The energy equation. Yeah, let us do that. Okay, so first we will do dimensional. Next we will do non-dimensional. So if it is there, you cut it, students. Don't worry. Okay. Okay. Boundary layer equations are, okay, the equations, governing equations, governing equations inside the boundary layer. Students, I want you to refer Sengel once. Okay, I want you to refer Yunus Sengel, page 399. Page 399. Okay, just read that. That's it. Nothing else. Just read that page 999 and just see here and there. That's it. Okay, up here and there in the page 399. Just refer to that page. Okay, what I'm writing here is directly from that page only, which is understandable. Okay, so we know that boundary layer equation, hydrodynamic boundary layer equation, or Prandtl's boundary layer equation, Prandtl boundary layer equations. What are those? We have dou u by dou x plus dou v by dou y is equal to 0. First one, correct. Second one would be u dou u by dou x plus v dou u by dou y, and we know dou u by dou x or dou square u by dou x square. By order of magnitude analysis, we have done that. You remember, dou square u by dou x square was found to be negligible. Remember Prandtl boundary layer equation? So if you consider Prandtl boundary layer equations, this part on this, if you say 2 dimensions, we are going with the 2 dimensions. When we go with the 2 dimensions, this is anyhow 0. We saw that dou square u by dou x square goes to 0 by order of magnitude analysis. So that is the one which is coming here, which comes as nu into dou square u by dou x square only. Okay, since dou square u by, sorry, dou y square only, I'm sorry, dou y square only, because dou square u by dou x square is equal to 0 by order of magnitude analysis, which we have done in our fluid mechanics. That's why I did that, because now I can rush through. So understanding, there's no problem. And the same thing is derived here. Prandtl's boundary layer equation is also done. Okay, they are told. Okay, they have not derived also here. I have only derived, but they have told. So if you see it, and also in Sengel there is one energy equation they have derived from the first principles. Just have a look at it. Okay, just have a look at it. Just like we derived continuity equation, we derived this heat conduction equation, whatever the what do you say? When I said heat conduction, what is the energy coming in, what is the energy going out? Similarly, they have done. So just do that. Now, boundary layer equation for thermal boundary layer. Okay, thermal boundary layer equation. Thermal boundary layer equation is given as same thing, u dou u, instead of dou u it is dou t by dou x plus v dou t by dou y is equal to nu dou square t by dou y square. Very, very, very important. Very, very, very important. Similar to this. Okay, so we can write these equations as we have gone with 6. So 7a, 7b.
Is it mu or alpha there?
Very sorry. Very sorry. Alpha. It's not new, it's alpha. Yeah. It is alpha into dou square v by dou y square, because it's equivalent. This is called very, 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 very infinity important. This is the base. This is the base. Everything is built on this one. Post convection heat transfer is built on that one. Easy. Of course, there is another one which is dou square p by dou y, dou square p by dou p by dou y is equal to 0, which I have ignored. So similar way, dou t by dou y is equal to 0. No, dou t by dou. It's not there. Only dou p by dou y is equal to 0. Temperature, no. Because there is a dou t by dou y. Okay. So there is no equivalent of pressure in energy equation. None. Written down, students. Now, let us look at the non-dimensional equations. If we consider non-dimensional equations, okay, if I consider non-dimensionalizing, okay, non-dimensionalizing, written down, no, finish, no, non-dimensionalizing, non-dimensionalizing, write it along with me, students, okay, convection equations, using x star is equal to x by L, which is the length, y star is equal to y by L, u star is equal to u by u infinity, v star is equal to v by v infinity, u infinity, I'm sorry, v by u infinity, and then p star is equal to p by rho u infinity square, pressure by u, right? And temperature T star is equal to T minus T surface, that is wall, divided by T infinity minus T wall. This is what we use as a non-dimensional. Okay. We obtain, you can do this one, I'll write the final equations. Don't have to spend time on things which is, you can do it. Okay, so next you will get dou u star by dou x star plus dou v star by dou y star is equal to 0. Another one you get is u star dou u star by dou x star plus v star into dou u star by dou y star is equal to 1 by Reynolds number with respect to length, is it not? Do we get Reynolds number with respect to length or with respect, yeah, we get in terms of length only. Reynolds number with respect to length, whatever the length is, okay, into dou square u star by dou y star square minus dp star by dx star. I have written d here, so why? This pressure is dependent only on x. It does not depend on y. Correct? And this is mass, this is mass, this is momentum, and then you should have energy. If you have mass and momentum, then of course you will have energy, right? So u star dou t star by dou x star plus v star into dou t star by dou y star is equal to, here you will get something called 1 by REL. The additional thing what you will get is Prandtl number PR. Very important. This comes as dou square T by dou X, dou square T by dou Y star square. Very important. So let us write this as very, very, very important. You say it as 8A, 8B, and 8C. 8A, 8B, 8C, where PR is equal to Prandtl number given as PR is equal to what is Prandtl number? It is nu by alpha. Is nu by alpha. Very, very, very important. As I said, there are number of questions on this based on Prandtl number only. Okay, so we'll stop it here, students, and the rest of the things we will see in evening class. At 6 o'clock class, we will look at more of convection. Fine.
In 7D equation, we didn't get the BP value.
Very, very sorry, very sorry, very sorry, very sorry, very sorry. Here you write minus dp by dx. Very sorry, that's mistake. That is a mistake. And 1 by rho. I'm sorry here. There is one mistake here, students. Big mistake. So it should be written. If it is not there, please write it. So 1 by rho dp by dx. Very important things which we missed. My bad. Okay, very important.
So next slide.
He has also missed. I think he has taken into consideration the Blazius solutions. In Blazius solution, dp by dx is not there, observe. So maybe he has taken Blazius solution over a flat flow. But anyhow, don't worry. Generally, it is there. Okay. Here he has not taken. In Blazius equation, dp by dx is not there. You remember that? He has used to derive it. Okay, derive the boundary layer thickness for the Blazius equation. But don't have to worry. In general, the dp by dx exists. Is it not? Okay. Thank you, students.